Welcome. Today, as promised, we're going to be looking at propositional logic using a replacement method. That means that we're going to be using the concept of replacement as the fundamental concept from which we will build up this entire system. But unlike the last video, which assumed you had some basic knowledge of propositional logic, we're going to start things off back at square one. And I do like to start things off with a parody of the first few lines from Lewis Carroll's Symbolic Logic. The universe is made of things, and some of those things we will call statements. Statements are things that are either true or false. For example, we could say the earth is round, the sun is bright, unicorns exist. Any of these things are things that are either true or false. And we may not know whether they are true or whether they are false, but they are either true or false. For instance, we could say, it's raining. And that would be a statement as well, despite not knowing whether it's true or not right now without looking out a window. To denote a true statement, we're going to use this symbol. You might notice it looks like a capital T. Sometimes we may call this top. And both of these are, of course, true. And to denote a false statement, we will use, well, if true is a capital T, then what must false be? If you guessed upside down capital T, you'd be correct. And sometimes we may call that bottom. Of course, unicorns do not exist, so we'll put that over there. I assume we use these symbols because at some point people realize that if you allow students to write either T's or F's, that you get a lot of things that look like this, which could either be a T or an F depending on how generous you want to be. In any event, when we say that two statements are of the same sort, that is, they are both true or both false, we say that they are logically equivalent. And we will use this symbol placed between these two statements to indicate logical equivalence. This is like our equal sign for statements. For example, we could say that the earth is round is equivalent to the sun is bright because they're both true, they're equivalent. And because we only will care about whether statements are true or whether they are false, we can take any true statement and replace it with any other true statement, and that won't change whether what we started with was true or false. So we will say that statements that are both true are replaceable with one another, and statements that are both false are replaceable with one another. But the statement that two things are equal is itself a statement. And that brings us to building statements out of other statements. Logical equivalence, or is replaceable with, or as sometimes we will call it, if and only if, is denoted by the double arrow we saw previously. For example, we could say, pigs fly if and only if unicorns exist, and that would be a true statement overall. We've combined the two statements into a new statement. And here we built up a bit of a table that shows whether statements like these are true or false. Notice that everything on the left-hand side of the table is equivalent to the corresponding thing on the right-hand side. So we might write the table like this, but for use as a reference for later, that might get a little bit confusing, so we're going to stick to the simplified table here. So if, for instance, you ever see a statement in the wild that says false is equivalent to true, then according to the table, you can simply replace that with a false. There are other ways that we can build up larger statements out of smaller statements as well. One that may have occurred to you is and. So let's say that the earth is round and the sun is hot. That would be true because true and true is true. But if I say the earth is round and unicorns exist, then I'm asserting one true thing, but I'm also asserting a false thing. And so overall, the whole statement is false. More formally, we can define the and operator using this table of equivalencies. Note that the only way for an and statement to be true is if both parts are true. In addition to and, another way of combining statements is with ors. For an example of how or statements work, let's imagine that I ask you to get me a hamburger or fries. If you bring me a hamburger and no fries, I'm happy. If you bring me fries and no hamburger, I'm happy. But what if you bring me both? Well, I'm still happy. I wanted at least one of those two things, and that's what I got. So as long as we have at least one true in an or statement, then it's going to be true. And the only way to get a false statement then will be to have both parts be false. It's worth noting that this is in contrast to the exclusive or, aka the either or, where both parts being true is not acceptable. The last way that we'll look at for combining two statements to get new ones is the if-then statements. Another way of saying if-then is with the word implies, which is a little bit less awkward because it goes in between of the two things instead of wrapping around them like the words if and then do. There are actually a large number of ways of saying if-then in the English language, but we'll save that exploration for a later video. The if-then, or imply statements, are the ones that cause people the most confusion, so I have two examples for us to go through here. The first one is, if it's raining, then the road is wet. So let's say that it's raining and the road is wet. So both parts are true. Is that possible? Yes, so true implies true is true. What about it's not raining and the road isn't wet? Is that possible? Yeah, so false implies false is true. And could it be raining but the road not be wet? No, that would be impossible, so true implies false is false. And lastly, and this is the one that causes the most confusion, if it's not raining, could the road be wet? Yes, of course it could. They might be testing the hydrants, for instance, or maybe it just got done raining, so false implies true is true. For our second example, let's say that a hot dog vendor has one rule. If you pay $5, then they will give you a hot dog. I tell them I don't have $5, and they give me one anyway. Did they break their rule? No, because the rule only says what would happen if I gave them $5. It said nothing about what would happen if I didn't, which is why false implies true is true. Of course, if I was the franchisor of this hot dog stand, I would probably want to change the sign to say, if we give you a hot dog, then you paid us $5. Or more fairly, perhaps, we will give you a hot dog if and only if you pay us $5. And this is the most common confusion with if statements, that in the colloquial language we often use if-then when we really mean if and only if. Mathematicians are very particular about this distinction, however, so we've invented a shorthand for if and only if that's just IFF, so that way nobody has an excuse for not using that instead, at least in writing. And here's a table for if-then statements. And note that the only way to make an if-then statement false is by having true implies false. So the setup happens, but the follow-through fails. Everything else will be true. There's a lot more that can be said about if-then statements. We could talk about necessary conditions and sufficient conditions, but I think I'll save that for a future video perhaps on translating things back and forth between English and propositional logic. And lastly, the one additional way of building a new statement out of an old statement is by using the not. Unlike the other ways, instead of taking two new statements and combining them, this just modifies a single statement. So we could say, not pigs can fly, and that would mean the same thing as pigs cannot fly. And you can think of the not as causing the logical symbol to flip over when you're evaluating logical expressions. So now we have all we need in order to start evaluating some simple propositional statements. All we have to do is simply find anything that we recognize and replace it with the simpler evaluated statement. So for instance, in this example, I recognize the true implies false. And I know that I can replace that with false. And then maybe I recognize that true or false is true. So I can replace that with just a true statement, and then I see that not true, and I can replace that with false. And then we are only left with false is equivalent to false, which we know, of course, that that is true, and so we are done. This is, for our purposes, what we'll call a proof of the original statement. Since the only thing that we ever did was replace things with equivalent things, each line is equivalent to the neighboring lines, and so we are confident that the first line has to be equivalent to the last line. The statement we started with happens to be true in this case, so we say we've proved that it's true. If it had been false, the last line would have been a false, and we would have said we'd proven it to be false. Let's look at another example. Not true and false implies false. Here the only thing that we recognize straight away is the not true, which we can replace with false. Then we have that a lie and another lie together make a bigger lie. And lastly, false implies false, which should be true. Now you may have noticed that although we are using 5 different operators in these expressions, we haven't had any need for anything like an order of operations. This is because we've made sure to use plenty of parentheses to make these statements clear. However, there are some unnecessary parentheses that we can drop as we get used to writing these statements. The first instance being that with not statements, instead of writing parentheses around a not statement, we're just going to say that the not only applies to the very next thing that's in front of it. So in the previous example, we can write not true and false as not true and false like this, which is not to be confused with not true and false, because the not will only apply to the statement directly in front of it. Another thing that is commonly done is to use blank space in place of parentheses. Actually, I always find it mildly funny that I will often see my students doing this on their own each year without my showing it to them. Evidently, it's a very intuitive thing to do, so I thought it would be worth mentioning. Parentheses are also often dropped around strings of the associative operators like ands and ors, but this can be a little bit confusing because they don't associate with each other, and also it's not common practice to apply this to logical equivalence, probably because such strings of equivalencies are rather unintuitive, asserting the falsehood of an even number of their constituent statements, but that's a whole other story. Okay, so this is all very clear and concrete, but what if we want to make statements in our logic that are a bit more general? For example, we might want to state that anything of the form P implies P or true is true for all possible statements P, whether P is the statement unicorns exist or the earth is round. So P here is like our variable. The way we say that P implies P or true is true for all statements P is for all P, P implies P or true. But we use the symbol of an upside down A to mean for all, so we actually just write upside down A, P, bracket, P implies P or true, end bracket. This upside down A is also called the universal quantifier. There's also what we call the existential quantifier that looks like a backwards E and would assert that, for example, there is some statement P that we could plug into P implies P or true in order to make it true. Or in other words, there exists a P such that P implies P or true. So with the universal and existential quantifiers, we can either say that a statement, no matter what is plugged into it, will always be true, or that it will sometimes be true depending on what is plugged into it. But of course, there are really only two types of statements that we'd plug in for the variable, true and false. So what the universal quantifier is really saying is that the statement will hold when we plug in a true for P and when we plug in a false for P. So here we have some statement involving for all P, and the dashes are just an informal way of indicating that P is involved in some larger, more complicated statement somehow. And as mentioned, if the statement, whatever it is going to be true for all P, then it must be true when we plug in a true and when we plug in a false. Thus, if we make two copies and replace all instances of P with true in the first copy and false in the second copy, and then place an and between the two copies, then we'll have successfully eliminated the universal quantifier. We can perform almost the exact same process in order to eliminate the existential quantifiers, but what the existential quantifier is saying is that when we plug in true and false, at least one of the statements will be true. In other words, the statements will be true when we plug in a true or when we plug in a false for the P's. So going back to the previous examples and performing this process, and remember that P is just a variable and we could use anything, but we'll continue to use P here as our arbitrary variable. So we'll make two copies of everything in the brackets, replace the P's with true and false, and of course we have our and in between. Then we recognize true or true as true and false or true as true, so replacing those, and evaluating the implications, and true is true. So there you go. For all P, P implies P or true is true. But what changes if we have a there exists? Well, the first step is nearly the same, but this time there's an or in between the two copies, and replace with trues and falses like before, and simplify like before, simplify, and this time the last step is true or true, but that is also true, so once again we find that this is a true statement. So let's look at an example with multiple quantifiers. So here we have for all P and for all Q, P is equivalent to Q implies that P implies Q. In order to verify this, let's focus on getting rid of the quantifiers one at a time. Now it doesn't actually matter which one we start with. Demonstrating that fact is one step in the proof of consistency for the system, which for now I will leave to the viewer. We've been getting rid of so many P's though, let's start off by getting rid of Q just to mix it up a little. So we're focusing on this for all Q statement. Everything outside of it is going to stay the same, and only what's inside its brackets is going to get duplicated. And this is a for all statement, so it's going to have an and in the middle there. Getting rid of the Q's because they are the variable that belongs to the quantifier that we're getting rid of, and replacing them with trues in the first copy and falses in the second copy. And there we have it. We've gotten rid of one quantifier. Now we're left with only one variable, P. We could now get rid of the P's quantifier and we would have this absolute mess, and we could simplify that down, which is a good thing to practice at first, but there's a better way to go about proving this statement without it getting quite so long. We have what we might formally call a replacement schema that simply says that if we've proven that two formulas are equivalent for all statements involved, then we can replace one for the other whenever we come across them in the wild, so long as the result is a well-formed formula. Here the symbols phi, chi, and psi are not part of the logic that we are building. They are metamathematical symbols that I'm just employing here to better convey to you the rules of the symbolic logic that we're looking at. Before getting back to our example, which will make this clearer, I'll really quickly touch on this last note about well-formed formulas. Well-formed formulas, or WWFs for short, are just what we call statements that make sense and can be evaluated to either true or false. As an example without quantifiers, the example from earlier of the ambiguous statement without parentheses would not be a well-formed formula, of course, because it's ambiguous. Here you can see some other examples of statements, some of which are well-formed and others are not. Pause the video here and identify which are which. And 3, 2, 1. Here are the incorrect ones. There's quite a lot that can be said about well-formed formulas, and they can be given a proper constructive definition, but in the interest of time, I'll leave that for another video if there's any interest. Okay, so let's look at an example of the replacement schema really quickly. Here's a statement which will be one of the collection of statements that we will call simplification rules, and here's its proof. Now let's go back to the previous example and see how using the replacement schema and this simplification rule can make our proofs a lot more condensed. So here's where we had gotten before, and instead of eliminating the for all p, this time let's use our simplification rule first. So here you can see the only change I've made was to replace the p implies true with true, which is exactly what our rule from before said was possible. Now the next thing we can do here is the part that people find confusing. We can replace the entirety of the left-hand side of this proposition with just true. And we're using the exact same simplification rule to do it, because the rule says that this works for any statement. It says that if we have thing implies true, then we can replace that with just true. And that p is equivalent to true thing, it's just a thing. So the statement in line 3 there just says thing implies true. And so I've replaced it with true. You might have noticed that I've also changed things on the right-hand side of the expression as well. There I've just used some simplification rules that we haven't seen yet, and using even more simplification rules, we can finish off the proof like this. And so you can see just how much more compact these proofs can be with the aid of 15 to 20 or so simplification rules. In the next video, we'll work with breaking down statements with multiple quantifiers and exploring some of the properties of quantifiers, as well as looking in more detail at all the different simplification rules that can help us prove things faster, and we'll see how to derive those.